Hi all, welcome back to yet another video of CSM 70 final review session. I'm Brian, I'm one of the CS70 cohorts for CSM. I'll be walking you through this video on discrete distributions. So we're going to be separating distributions into two separate parts, discrete and continuous. Discrete is going to be a lot shorter compared to continuous, but it's still as important. So for discrete distribution, there's three key distributions for you to remember. We might be able to add in Bernoulli right here as well, if you wish. But Bernoulli is probably the most simple distribution you can think of, and we didn't include it because it's not as interesting. And then we have binomial, we have geometric, and Poisson. You probably know all of these, but let's just do a brief recap of what they mean. So binomial distribution, you have two arguments, so this is how you usually write it. Binomial of n comma p, so you have two variables. N is the number of tosses, the number of trials, and p is probability. The trial is a success. And here we have all the expectation and variance. To give you an idea, to give you a more concrete idea of what's going on, I'm going to be using the analogy of coin flipping throughout this entire time. So for binomial, it's like flipping n coins such that they have each coin has a probability p of flipping heads. In other words, each coin is a Bernoulli random variable. Each coin is Bernoulli with p. And we have the expectation and variance. The expectation makes a lot of sense because if you flip n times with probability of heads of p, you expect the expected number of heads to be n times p. Likewise for variance. Okay, let's move ahead to geometric. So geometric is a very similar story. So the story here is I have a coin that flips heads with probability p. And the question is, how many times do I flip until first heads? And our equation here makes sense because we flip tails x minus 1 times, and then we flip heads in our last one. And the expectation and variance just follows. That's geometric distribution. Let's go on to Poisson. So Poisson is a little special. It only takes in a lambda. It's very special because we actually say that lambda is equal to n times p, where n is really, really large. It goes to infinity. And p is really, really small. So Poisson distribution is basically taking these binomial geometric to infinity. And we have expectation and variance that follows from these definitions. Okay. So let's just move on ahead. That's Poisson distribution. But for Poisson, it's very hard to give an interpretation in terms of coin flipping. Because you don't have a coin that flips heads, with a probability of 0. Instead, what we usually go for are things like the bus arriving at a bus stop. or something like a reaction happening between two atoms. So what's the probability that these two particles collide? That's where we usually use Poisson. So let's say 50 on B comes an average 2 times per hour. I'm going to give a real life example just for this one. 2 times per hour. Find the probability that 50 on B comes 3 times between 350 and 450. So there'll be an example of using a Poisson distribution. Okay, so in this case, we just plug it right in. So we say, okay, we have base unit of time is 1 hour, so x is equal to 3. And therefore, so meaning we want it to come 3 times during this 1 hour. Probably x is equal to 3 is e to the minus 2. Minus 2 comes from this rate. So we actually call this lambda over here to be the rate. The rate is 2 times per hour. So we just put the lambda is equal to 2 into the equation, and we get our probability. So this is a subtle note that comes useful sometimes. If you have two random variables, x and y, such that they're distributed as a Poisson with, I'm going to make it lambda 1 and lambda 2, then it becomes lambda 1 plus lambda 2. X plus y is distributed that way. Okay. One other thing that I do want to note about geometric is that this has a memoryless property. So what does this mean? This means that, okay, say I flip my coin. So I flip my coin k times. Now on the k plus ones, you might think, hey, I flipped it k times, I only got tails. K plus 1 must have a really high probability of it being heads. Well, the memoryless property says, okay, we just reset. Once we get to k plus 1, we reset. K plus 1, we reset. So every single time we are resetting. We are resetting our chances. So what this means, if I put it more formally, is that probability of x, given that I've seen k, is the same as probability of x, right? Let's actually put this a little more formally. Probability that x is equal to k. Let's probably not put k. Let's put x. Is equal to the probability that x is equal to x plus k, given that I saw k. Alright, so that's the memoryless property for you, and it's going to come up again in exponential distributions. Perfect. Let's move on and go to a new question. Consider an urn with 3 blue balls and 1 red ball. Suppose you sample 1 ball at a time with replacement. Let x be the number of draws required until both of the colors, blue and red, have been observed at least once. What is the probability x is equal to n? The first ball is red, 4, and is greater equal to 2. And what's the probability x is equal to n? Okay, so we need to draw until we see both colors. This seems to suggest to us that maybe we should use the geometric distribution. So for part A, we are given that the first ball is red, so we've seen red. Notice we see red. So from 1 to n, we just need to see blue. We need to see blue. Okay, so it's going to be a geometric distribution going from 1 to n, such that we see blue color. Now, we see blue with a probability of 3 over 4, and we see a red with a probability 1 over 4, right? So let's go right here. We see red with probability 1 over 4. We see blue with probability 3 over 4. which means, I'm going to write this down. Probably x is equal to n given red. This is exactly, I see red in the beginning, so I put a 1 over 4 there because that's what I've seen. And then for the n minus 1 cases, my final one is going to be 3 over 4. But I'm going to see 1 over 4 n minus 2 times until I get to 3 over 4. Why n minus 2? Because I already seen it once. So this is 1, this is n minus 2, this is 1, and once you add them up, you get n. So this is our final probability. Okay, let's move on to the next one. Probability x is equal to n for n is greater than or equal to 2. Now for this one, we're going to be a little smart on this one. We're going to say the probability at x is equal to n is actually equal to, we're going to use a common trick back from the base, if you remember video 1. Given red, given first ball is red, plus probability x is equal to n, given first ball is blue. Not entirely true just yet. I forgot one part out of this. Given the probability red, probability blue. Right? Let's fill the parts in. For the first one, we already have it. So we can just write that down. n minus 1. I was a little wrong here. We actually don't need this. I was thinking too ahead. The reason we don't need that is because we already given that the first ball is red. So we don't need that probability. Apologies on that. So we have 1, 4, n minus 2, 3 over 4. Multiply that by 1 over 4. I was thinking a little ahead to this question. Apologies again. Plus probability x is equal to n given blue is going to be, I'm going to use the same tactic as I did before. I only see blue n minus 2 times, and my final one is going to be 1 over 4. Probability of blue is 3 over 4. I just calculate that, and that should give me my answer. Perfect. Let's move on ahead. And we did have a simplification right here, but I'm not going to simplify it. If you wish to, go ahead. Actually, let me do the simplification for you. The denominator stays the same for both these summations. This is going to be 4 to the n. This is also going to be 4 to the n. We have a 3 because 1 to the power n minus 2 is just 1. There's 3 n minus 2. And then we have a multiplied by 3. Okay, so 3 plus that, we have 3 times 1 plus 3 n minus 1 over 4. Perfect, and that's it. Perfect, so this was discrete distributions. I hope you've enjoyed the video, and I'll see you on the next one, the final one on continuous distributions.